Welcome, and thank you for joining this webinar. From Connectivity to Understanding, the Semantic Future of AI Communications, prepared by the Alpert Research Team. Wireless networks were designed to move bits efficiently, but future systems must also understand meaning, intent, and context. Semantic communication is emerging because AI, autonomy, XR, and industrial automation require smarter, not just faster connectivity. It enables networks to prioritize relevance over raw data volume, improving efficiency, responsiveness, and value. For 6G, this may become a foundational capability. We're going to lay out a comprehensive technical and strategic roadmap for you.
We're going to move from the hard physical constraints of our current networks into the new mathematics of semantic information theory.
And then deep into the AI-native engineering of 6G architecture. And finally, we'll explore exactly how you commercialize, standardize, and deploy this technology. What exactly is semantic communication, or SEMCOM? Fundamentally, it's a departure from transmitting raw data. We're used to transmitting pixels for a video or audio waveforms for a voice call. SEMCOM abandons that. It shifts to transmitting the underlying intent or meaning of the source.
It completely, deliberately abandons the requirement to perfectly reconstruct the original data at the destination. Its entire focus is on whether the receiver understands the meaning well enough to execute a very specific task.
And the reason we're being forced to abandon the idea of perfect digital reconstruction is what the sources call the 6G scale problem.
As we look toward the 2030s, data volumes are projected to grow by up to 1,000 times relative to what we see on 5G today. We aren't just talking about a few more people watching streaming video in high definition.
No, we're talking about massive, dense industrial IoT swarms on factory floors.
An immersive, real-time extended reality, or XR, and fleets of autonomous vehicles constantly pinging each other. Traditional telecom's answer to data growth has historically been brute force. Just build wider pipes.
Buy more spectrum, build more towers, install more fiber.
But that brute force approach is no longer economically or physically viable. The massive energy consumption required to modulate and transmit that sheer volume of raw, pixel-perfect data would eventually require us to build dedicated power plants just to run our cell towers.
So SEMCOM represents the foundational layer for intelligent services that require cognitive intent. It completely shifts the network's role in society. For decades, a telecom network has been a passive data relay. It's just a dumb pipe shoving water from point A to point B without caring what's in the water. Semantic communication turns the network into an active meaning management system.
And what you really need to understand about the current state of this technology is that it's rapidly transitioning out of the laboratory. It's moving into the intrinsic, native capabilities of future wireless systems. We're completely reframing what a cellular network is considered to be. This isn't an optional software application that sits on top of the network. It's being baked into the core physical layer of how radios talk to each other.
Think of traditional telecom networks like a very stressed out, highly secure courier service that is tasked with protecting a massive wooden crate. Now, inside this crate are thousands of foam packing peanuts, yards of crumpled newspaper, and buried at the very bottom is just one single ordinary hammer. The traditional 5G network protects that crate with its life. It burns a ton of jet fuel, takes up a massive amount of cargo space, and flawlessly delivers every single useless foam packing peanut to your front door without a single scratch.
Under our current engineering rules, the network must assume every single piece of foam is a vital, life-saving piece of information.
But a semantic network operates like a completely different kind of courier. This courier opens the box, looks inside, understands that you are building a house and just need to drive a nail, throws away the crate and all the packing peanuts, and just hands you the hammer. It's revolutionary in terms of saving resources. If we intentionally stop measuring whether every single bit arrived perfectly, doesn't that shatter how we evaluate success in telecommunications?
That is the exact friction point the entire industry is wrestling with right now. Technically, yes. Under the classical rules of telecommunications, throwing away parts of the original file means it is a corrupted, failed transmission. And to understand why the brightest minds in wireless are suddenly perfectly okay with corrupted files, we have to look at the foundations, to a man named Claude Shannon.
Everything we use today, from Wi-Fi to Bluetooth to 5G, is built on his math.
While working at Bell Labs, Shannon published his mathematical theory of communication, which established what we now call classical information theory. He was trying to solve what we refer to as Level A, the technical problem of accurately transmitting symbols over a noisy, imperfect channel. But to make his brilliant mathematics work, Shannon made a very specific, deliberate choice. He explicitly decoupled the meaning of a message from the engineering problem of transmitting it. He essentially said, the meaning of the message is irrelevant to the engineering of the wire.
Under Shannon's separation theorem, a network treats a beautiful Shakespeare sonnet and a blast of absolute random static exactly the same. Doesn't read the poem, it just counts the ones and zeros and makes sure they match on the other end.
But literally a year later, a mathematician named Warren Weaver proposed a broader tripartite model. Weaver said, yes, Shannon's level A is the technical problem and it's brilliant, but there are two other levels we are ignoring. There's level B, the semantic problem. How precisely do the transmitted symbols convey the desired meaning? And level C, the effectiveness problem. How effectively does the received meaning influence the receiver's conduct in a goal-oriented context?
So level C is basically asking the ultimate question. Did the autonomous car actually stop before hitting the child? Not did the video load? Did the goal get achieved?
It's about goal achievement, not just symbol delivery.
If Warren Weaver laid this out in 1949, and it makes so much sense, why did we build 1G, 2G, all the way up through 5G entirely on Shannon's level A, leaving the meaning of the data on the cutting room floor?
Because the industry had absolutely no choice. The computational power required to mathematically extract and quantify intent or meaning simply didn't exist in 1950 or 1980 or even 2010.
Because it's a massive computing problem.
Huge. You can build a relatively cheap, simple electrical circuit to count discrete ones and zeros. You could not build a copper wire or a basic microchip that evaluates the philosophical intent of a photograph. Artificial intelligence, specifically deep learning and neural networks, is the missing computational substrate that finally makes Weaver's vision operational today.
And it's arriving exactly when we need it, because we're hitting a massive brick wall. The industry called it the Shannon limit, or the capacity wall. The sub-6 gigahertz spectrum is completely hopelessly saturated. And if we try to escape that by using much higher frequencies, we face severe physical propagation challenges. Those tiny waves get blocked by tree leaves, they bounce off buildings, they even get absorbed by heavy rain. We literally cannot brute force our way out of this data crisis by just finding more spectrum.
And you have to remember who these networks were built for. 5G was fundamentally human-centric. The ultimate gold standard test of a 5G network was streaming a pixel-perfect 4K video to a smartphone so a human eyeball could watch it without noticing a glitch. 6G is machine-centric. Machines don't have eyeballs. The machine's algorithm only needs velocity, trajectory, and crash probability.
If the receiving machine gets a transmission where 90% of the original bits, all the visual packing peanuts, have been intentionally thrown away, how does a telecom engineer actually measure success? For 50 years, the ultimate dashboard metric for a network operator has been the bit error rate. You send 1 million bits, and if only 2 bits get flipped by static, you get a gold star. But if we aren't counting bits anymore, what replaces Shannon's math?
This brings us to the new underlying science. Semantic Information Theory, or SIT. We are entirely moving away from measuring bits to measuring meaning, and the foundational mathematical concept that makes this possible is called synonymous mapping.
Let's use a really simple example to illustrate how backwards this is from classical engineering. Take the words car and automobile.
Okay.
In classical bit-centric systems, if you look at their ASCII binary codes, the ones and zeros that make up those letters in a computer, they are completely fundamentally different. If a classical network drops a single bit and accidentally turns the word car into tar, the transmission is ruined. The engineer logs a failure.
Because classical Shannon entropy measures the uncertainty and the exact syntax of the symbols themselves. It cares about the spelling.
But in semantic information theory, the words car and automobile belong to the exact same equivalence class, because the vehicle's braking algorithm reacts identically to both words. It doesn't care which one you use, the result is the same. Semantic entropy is actually much lower than Shannon entropy. Because multiple vastly different bit patterns can convey the exact same meaning, there's inherently less uncertainty about the meaning than there is about the syntax.
Which redefines the telecom business entirely. Network operators are currently redesigning their command centers. They're moving away from traditional metrics like bit error rates, or BER, and peak signal-to-noise ratio, PSNR. They are adopting semantic KPIs. It allows operators to extract vastly more utility and action out of the exact same limited physical spectrum, which drastically lowers the cost per bit for actionable intelligence.
The sources state that semantic channel capacity can mathematically exceed classical Shannon capacity.
I know, it sounds impossible.
How is that possible without breaking the laws of physics? Shannon's limit is like the speed of light for data. You cannot physically push 10 gigabits of data through a 1 gigabit pipe.
It's a brilliant paradox, and you are right to be skeptical, but we aren't breaking physics at all. We are exploiting semantic redundancy. Imagine 10 different 4K security cameras all looking at the exact same stop sign at an intersection, just from slightly different angles. Syntactically, under Shannon's rules, those are 10 drastically different, massive video streams. If you try to push all 10 raw videos through a local cell tower simultaneously, you hit the Shannon capacity limit immediately. But semantically, what is the actual actionable value of those 10 massive video streams to a connected car's braking system? The value is just a single binary state. Stop. That's That's it. In a semantic network, we collapse the state space of the data before it ever enters the pipe. We extract that one vital semantic token, the command to stop, and we transmit only that tiny token. So we effectively widen the channel through contextual intelligence. The channel's capacity to deliver actionable intelligence vastly exceeds its physical capacity to deliver raw bits.
We aren't making the pipe bigger. We are just drastically reducing the size of what goes into the pipe by boiling it down to pure meaning. So if we are tossing out the bit error rate dashboard, what are the new vital metrics that a 6G network engineer will actually be tracking?
The primary semantic KPI replacing bit error rate is task success rate, or TSR.
Meaning, did the machine actually do what we wanted it to do?
Yeah. If the network sends a command to a robotic arm to pick up a fragile silicon wafer, the network doesn't care if a few pixels of telemetry data dropped out over the Wi-Fi. The only question that matters is, did the robot grab the part without shattering it? If yes, the transmission was a 100% success. Another critical metric is latency to meaning.
Traditional latency just measures the milliseconds it takes a packet to fly through the air from the cell tower to your phone.
L2M includes the cognitive processing time because you aren't just sending simple data anymore. The AI at the receiving end has to actually think about it. It has to unpack that semantic token and decode the intent. So L2M measures the total time from transmission until the moment the receiving machine fully understands the command.
New metric is the age of incorrect information, along with the value of information.
It's a crucial concept. Imagine an industrial boiler in a chemical plant. It sends a critical temperature reading of 300 degrees. But there's a network jam, and that data packet gets delayed in a router for an hour. Classical 5G network finally delivers it, checks the bits, sees they are in perfect order, and logs a completely successful transmission. But semantically, that hour-old reading is not just useless, it is actively dangerous if the safety systems rely on it. Its age of incorrect information is simply too high.
Under classical rules, the network is perfectly happy to deliver an old deadly message as long as the spelling is correct.
The new semantic network dynamically balances all of this. It constantly weighs latency, task error probability, and communication cost using a multidimensional mathematical tool called a goal-oriented tensor. It manages these variables microsecond by microsecond, deciding what information is actually valuable in the moment.
Okay, the math on the whiteboard is elegant. It proves we can squeeze vastly more meaning into a saturated channel. But let's bring this down to the hardware level. A standard copper wire or a silicon antenna doesn't know what a car is. It doesn't know what a stop sign is. It only understands voltage and radio waves. So how does a physical microchip actually execute this new math? How do we build a radio that understands intent?
This requires us to dive into the core engineering.
The traditional 5G setup inside your smartphone right now is highly modular and segmented. Take a picture. First, it goes to a source coder, like a JPEG or BPG compression algorithm, to squish the file size down. That algorithm is inherently lossy. It throws away some visual detail. Then, that compressed bit stream goes down the line to a completely separate channel, coder like LDPC or polar codes.
And the channel coder's only job is to add redundant mathematical protection bits so the data survives the static in the air. It actually bloats the file back up.
And finally, it goes down the line to a modulator, which uses a scheme like QAM, to translate those discrete ones and zeros into analog radio waves that fly out of your antenna. It is a rigid assembly line where each station is completely blind to what the other stations are doing. The JPEG algorithm doesn't know how much static is in the air, and the modulator doesn't know it's a picture of a dog.
But semantic communication uses a breakthrough called Deep Joint Source Channel Coding, or Deep JSCC.
This replaces that entire inefficient multi-step assembly line with a single end-to-end differentiable neural network.
So an AI handles the entire process, from the raw pixel hitting your camera sensor all the way to the raw radio wave leaving the antenna.
The deep JSCC encoder takes high-dimensional input, like the millions of pixels in an image, and the neural network extracts the essential semantic features. It finds the meaning. But instead of turning that meaning into binary ones and zeros, it maps those features directly into continuous valued channel symbols. It outputs a continuous mathematical tensor that directly dictates the amplitude and the phase of the radio wave. It skips the binary translation entirely.
And the efficiency gains are massive. The research shows a 2 to 5 decibel improvement over 5G baselines, especially in really poor noisy environments with low signal-to-noise ratios. But even better than the efficiency is how it handles failure. It eliminates what engineers call the digital cliff effect.
Everyone listening has experienced the cliff effect on a bad Wi-Fi call or a Zoom meeting. The video is absolutely perfect, and then you walk a few feet further from the router, and the video instantly turns into a glitchy, blocky, frozen mess.
Because digital systems are brittle. If you lose the exact sequence of ones and zeros, the entire file corrupts. But deep JSCC replaces that brittle digital cliff with graceful degradation.
Right.
Because it's transmitting continuous features, not fragile bits. As the signal gets weaker, the meaning just slowly becomes fuzzier. Think of looking at a painting through fog. The sharp details might blur, but the core intent, the subject of the painting, survives much deeper into terrible network conditions.
Generative JSCC, or GJSCC. This leverages incredibly powerful generative AI, specifically at the receiver. Generative JSCC involves transmitting incredibly tiny, microscopic latent seeds. Let's say I want to send you a high-resolution photo of a bird. Instead of sending the millions of pixels, the AI transmitter extracts a few continuous valued mathematical tokens that represent the pure concept. Bluebird, oak branch, morning light. It sends just those tokens.
And then the receiver on your device uses a generative model, like a diffusion transformer or DSCC, but running natively on the radio chip to regenerate or literally hallucinate the high-fidelity details locally. It prioritizes semantic consistency over exact raw data recovery. It doesn't care if the leaves on the branch are in the exact same mathematical position as the original photo, as long as the meaning is identical. This can achieve a 99.98% reduction in transmission overhead.
You are practically sending nothing at all. You are just whispering an idea to the receiver, and the receiver builds the reality. Now, the sources do mention a technical hurdle called the channel mismatch problem. If the AI was trained at a perfect laboratory with a great signal-to-noise ratio, but deployed in a real-world city with terrible interference, its performance drops.
Which is why researchers are developing solutions like robust information bottleneck training, which forces the AI to focus only on the most resilient features, and adaptive mechanisms that dynamically adjust physical layer parameters based on real-time feedback from the environment.
We are talking about replacing perfectly engineered, mathematically verifiable digital communication with a fluid, hallucinating neural network.
It's a valid concern.
What if the network encounters something totally outside its training data? If the AI transceiver on an autonomous car was trained exclusively on highways in sunny California, and it suddenly drives into snowy Canada and sees a massive moose standing in the road, won't it confidently guess wrong? Won't the receiver hallucinate a clear road because it doesn't know what a moose is and cause a fatal crash?
That is the most critical vulnerability in this entire paradigm. It is the absolute danger of semantic communication, and it's exactly why deep JSCC cannot and will not exist in a vacuum. To prevent those fatal hallucinations, both ends of the transmission, the sender and the receiver, must share a continuous, deeply synchronized understanding of the world. In the architecture, this is formally known as a knowledge base, or a KB.
So the transmitter and receiver must operate from the exact same dictionary. Imagine you and your best friend have an inside joke about a disastrous dinner party 10 years ago. I can walk up to you and just say 3 words, the spaghetti incident. Instantly, those 3 words trigger gigabytes of visual, auditory, and emotional memory in your friend's brain. You just transmitted massive amounts of data using almost zero bandwidth because you share a deeply synchronized knowledge base. But if I walk up to a total stranger on the street, someone without that shared knowledge base, and say the spaghetti incident, they are completely confused.
In telecom engineering terms, that confusion is called semantic noise. The latent seed, those 3 words, means absolutely nothing without the shared context. And in network design, we see 2 main scenarios for maintaining this context: symmetric knowledge bases and asymmetric knowledge bases.
Symmetric is the ideal scenario where they are perfectly matched, like a robotic arm on a factory floor and the edge server running it. They share an identical static digital twin of the factory. Because they both know exactly what the room looks like, they only ever need to transmit the deltas, the tiny anomalies or changes in movement, to each other.
But the real world is messy. This creates asymmetric KBs.
Because the environment changes.
The devices are highly mobile, their local environments change, and the AI models suffer from what we call semantic drift. The dictionaries become misaligned. The car in Canada is using a different dictionary than the tower in California,
which creates a massive logistical nightmare. The compute communication trade-off is incredibly real here. Think about a $2 IoT sensor running on a tiny coin cell battery strapped to a bridge to monitor structural vibrations. That tiny sensor cannot run a massive foundation model, and it certainly doesn't have the memory to store a continuously updating global knowledge base.
This brings us to a major strategic shift: semantic edge computing, or SEC. We have to split the cognitive workload across the compute continuum. We let the lightweight IoT device do what it does best. It runs a highly pruned, tiny, energy-efficient neural network whose only job is to extract the bare minimum latent vector. the basic intent. But the heavy lifting, the generative hallucination, the complex decoding, and the burden of maintaining that massive knowledge base is handled by the multi-access edge computing, or MEC node, which is physically located at the base of the cell tower where power and compute are plentiful.
But that still leaves the problem of keeping all these supercomputers synchronized. You have millions of massive AI dictionaries spread across the country. How do you synchronize them over the air without immediately clogging the exact same bandwidth they were designed to save?
That is solved through federated learning. Instead of sending massive files of raw data to update the dictionaries, the towers only share tiny mathematical model gradients, basically, the mathematical essence of what they just learned. They also use secure synchronization protocols like blockchain-anchored deltas to verify and keep the KBs perfectly aligned across the entire network without transmitting heavy raw data.
To make this viable in the real world, the telecom industry is moving toward an architecture called semantic edge computing. We cannot rely on data traveling all the way to a centralized cloud in Virginia to be semantically decoded. The latency would be disastrous. In a 6G environment, operators will deploy massive compute clusters directly at the edge of the network, physically located at the cell sites or regional hubs. These edge servers will host the primary knowledge bases.
We have public knowledge bases and private knowledge bases.
A public or shared KB serves an entire geographical area or application class. Imagine a highly detailed, centimeter-accurate 3D digital twin of a city's road network. But this KB is stored on the edge server and pushed out to every autonomous car entering the city limits.
Okay, so what's a private KB?
A private KB, on the other hand, is specific to a single user or session. For that autonomous car, the private KB might contain the exact trajectory, speed, and braking history of the vehicle over the past 10 seconds.
Because the network and the car share both the public map and the private history, the car does not need to constantly broadcast its location using heavy coordinate data. It only transmits the tiny semantic intent of its next maneuver.
And the edge server, using the shared KBs, instantly calculates the precise physical outcome.
This brings us to the most advanced form of this technology, generative semcom.
Generative semcom is where the line between communication and creation blurs. In this paradigm, the receiver is not merely decoding a message, it is actively running a reasoning engine, often utilizing advanced diffusion models or localized LLMs. The transmitter evaluates a scene and sends an incredibly sparse set of tokens over the air.
You are sending a live video feed of yourself sitting in a park. Your phone extracts a few semantic tokens: smiling person, sitting on a bench, sunny day, oak trees in background. It transmits almost 0 pixel data.
The edge server receives those sparse tokens. It feeds them into its generative AI model, cross-references its knowledge base regarding what oak trees and park benches look like under sunny lighting, and literally hallucinates the non-essential details. It synthesizes the leaves on the trees, the texture of the wood on the bench, and the exact hue of the sky.
You have just saved 99% of your network bandwidth, avoiding the Shannon limit entirely. And the human being looking at the screen on the other end sees a high-definition, perfectly realistic video stream. The AI painted the background because the specific arrangement of the leaves simply does not matter to the intent of the communication, which was just seeing your smiling face.
The shared context does the heavy lifting, allowing the radio transmission to remain incredibly light. Let's look at the network architecture. If I'm a major operator, how do I actually implement this? Do I just rip out the classic OSI model that has governed the internet for decades? Does the entire protocol stack just go in the garbage overnight?
No, it's absolutely not a rip and replace scenario. You can't break the internet to upgrade it. It involves building parallel planes. The literature defines a specific 3-layer SEMnet architecture that sits alongside traditional systems.
Layer 1 is the cognitive sensing layer. What's interesting here is that it doesn't just passively collect data like a traditional antenna. It actively infers user intent and uses generative AI to constantly discover new knowledge in the environment.
Then you move up to layer 2, which is the semantic transmission layer. This is the engine room. This executes the deep JSCC we discussed earlier. It maps the features to latent tensors, formats them, and physically routes them over the air interface.
And finally, layer 3 is the control and application layer. This is the management suite. It handles the knowledge-based synchronization we just talked about. It orchestrates tasks based on intent and manages network slicing.
This architecture is what completely transforms telecom carriers. They are evolving from being utility providers of dumb connectivity pipes into operators of intelligent information platforms.
So when a telecom engineer looks at a diagram of the 6G stack, what does this actually look like functionally?
Strategically, it manifests as the introduction of the semantic intelligence, or SI plane. In current 5G networks, we have the user plane, which carries your streaming video, and the control plane, which carries the signaling data to keep the network running.
Okay.
In 6G, the SI plane runs parallel to them, acting as the cognitive, AI-driven engine of the entire network.
If the SI plane is running the show, if the semantic noise gets too high, what is the backup?
There is always a hard-coded operational fallback. If the semantic link fails, say the confidence score drops too low, or a safety-critical anomaly is detected that the knowledge base doesn't recognize, the system instantly drops the semantic link entirely. It falls back and opens a classical, robust, old-school bit pipe to transmit and verify the raw data pixel by pixel. Furthermore, they deploy software called monitor agents. Their sole job is to log the latent space activations inside the AI so that human engineers can later mathematically audit and explain exactly why the AI made a specific decoding decision.
We aren't completely abandoning the classical bit pipe during the transition. It's a hybrid approach. But as we move into the actual integration with 5G Advanced and 6G, we are seeing AI-native air interfaces starting to replace the handcrafted mathematical waveforms that engineers have used for decades. The networks will literally learn the best way to transmit data based on the specific hardware and environment they are in. To deploy semantic communication at scale, we must examine the evolution of ORAN, the Open Radio Access Network. Historically, building a cellular network meant buying monolithic proprietary equipment. If a telecommunications operator bought a base station from a major vendor, they bought a closed black box. The specialized radio hardware at the top of the tower and the baseband software processing the signals at the bottom were inextricably locked together by proprietary interfaces like CPRI.
You could not mix and match. You couldn't buy a cheap radio antenna from a startup and run it using advanced AI software from Google. You were locked into the vendor's ecosystem.
ORAN shatters that lock-in. It deliberately decouples the hardware from the software. It standardizes the interfaces between the radio unit, the distributed unit, and the centralized unit. This allows operators to use commercial off-the-shelf servers, standard cloud computing hardware to run their radio networks as virtualized software functions.
And the true brain of this new open architecture is a component called the RIC, the RAN Intelligent Controller.
It enables network operators, or even third-party developers, to deploy AI-driven software applications to manage the radio spectrum resources in real time.
As we look towards 6G, the literature introduces an evolution of this concept, the semantic RIC, or SRIC.
In a traditional 5G network scheduler, if 10 users simultaneously request data, the network essentially attempts to divide the physical resource blocks of the spectrum equally.
The SRIC abandons that egalitarian bit-level approach. It allows the network to allocate radio spectrum based on a semantic grade of service.
It executes specialized algorithms known as semantic apps. These apps operate on a sub-millisecond control loop. They analyze the incoming traffic flows and prioritize them not by file size, but by information value and task importance.
Imagine the network scheduling system as a triage nurse in a crowded hospital emergency room. In a traditional network, the triage system operates on a strict first-come, first-served basis, treating every patient exactly the same regardless of their condition.
The traditional network honors the size of the data in the order of arrival, not the severity of the intent.
The semantic RIC transforms the cell tower into a master triage nurse. The SRIC instantly evaluates the semantic intent of the data packets. It sees the massive VR gaming download, registers its low strategic importance, and places it in the waiting room, allocating it lower priority spectrum. Simultaneously, it registers the tiny braking signal from the autonomous card, recognizes the critical information value, and instantly clears a dedicated, interference-free path straight to the operating room. And it manages this complex prioritization autonomously, evaluating thousands of intents per millisecond.
This capability fundamentally alters the monetization strategies for telecommunications operators. For years, operators have struggled to increase their average revenue per user, or ARPU, because they have been relegated to selling dumb pipes. They sell a pool of gigabytes, and the tech hyperscalers, the Googles, Apples, and Metas, capture all the value by running intelligent services over the top.
The SRIC allows operators to reclaim that value. They can begin monetizing the intent. A telecom operator will no longer just bill an enterprise logistics company for the terabytes of data their drone fleet consumes. They will offer a guaranteed service level agreement, an SLA, promising a 99.99% task success rate for collision avoidance.
They transition from selling raw connectivity to selling cognitive services and guaranteed business outcomes. The economic value shifts from the width of the pipe to the AI intelligence orchestrating the traffic within the pipe.
And this brings up a massive, potentially multi-billion-dollar business barrier, interoperability.
Oh yeah.
If a Samsung-built AI encoder on a smartphone tries to talk to an Ericsson-built AI decoder on a cell tower, but their neural networks were trained differently and their latent spaces are mismatched, it creates massive semantic noise. The system fails.
Because they're using different dictionaries.
Bridging these multi-vendor environments requires the development of universal linear aligners and semantic channel equalization to translate between different AI models.
Which means we desperately need universal global standards. How is the 3GPP, the global organization that actually writes the rules for cellular networks handling this transition.
The 3GPP standardization cycles are already meticulously mapped out. We are currently entering Release 20, which covers 2025 to 2027. This phase is heavily focused on study items, establishing the foundational feasibility of AI-native air interfaces in something called ISAC, or Integrated Sensing and Communication.
Then we move into Release 21 from 2027 to 2028, which begins the serious normative work. This initiates the first actual binding 6G specifications, rules for AI lifecycle management across the network, and the official definitions for semantic quality of service.
And finally, Release 22 and beyond, targeting 2029 and into the 2030s, will see fully integrated semantic compute orchestration deployed at scale.
The 3GPP 6G study is actually aiming to develop a non-backward compatible radio access technology. That is a massive break from telecom tradition. Usually every generation supports the last one, but they want to simplify the system design from the ground up to support this ubiquitous intelligence natively without the baggage of 4G and 5G legacy code.
The ITUR IMT 2030 framework, which is the guiding vision for 6G, designates ubiquitous intelligence as a key, non-negotiable design principle. Intelligence must be embedded deep in the core physical layer natively. It cannot be added as a software overlay later. In our traditional networks, interoperability is guaranteed by strict, immutable mathematical standards.
But semantic communication abandons those strict mathematical guarantees. It relies on deep learning models, highly subjective latent spaces, and dynamic shared knowledge bases.
This creates a terrifying scenario regarding vendor fragmentation.
If the underlying ontologies, the fundamental ways the AI models mathematically represent meaning, are not aligned, you experience catastrophic semantic noise. The latent spaces mismatch. The communication completely shatters.
If the tech giants refuse to share their exact proprietary knowledge bases due to competitive advantage, the global semantic ecosystem fragments. Your device might only be able to perfectly understand other devices from the same manufacturer.
Preventing this requires the development of a unified global semantic ontology. The IEE and the ITU are currently debating how to build semantic translation layers or linear aligners that can seamlessly map the intent from one vendor's ecosystem to another in real time. It is an unresolved diplomatic and engineering challenge.
And beyond vendor alignment, there is the problem of temporal alignment. But what happens when culture, language, or environments evolve?
We encounter context drift or model drift. If the underlying context of the world changes, the semantic decoder, relying on outdated priors, will fail to extract the correct meaning.
If an older adult hears a teenager use a new slang term, their syntactic reception is perfect. They hear the exact syllables and consonants perfectly, but they completely fail to extract the semantic intent because their internal mental knowledge base hasn't been updated with the new cultural definitions. The syntax succeeds, the semantics fail.
Networks will face the exact same problem on a global scale. As the physical environment changes, new buildings erected, traffic patterns altered, new visual anomalies introduced, the knowledge bases distributed across millions of edge servers and billions of consumer devices must be constantly and dynamically updated. Implementing federated learning systems capable of keeping the world's semantic models perfectly synchronized without consuming all the bandwidth we just saved is a monumental task.
And that leads directly to the physical constraint of computing power. We have praised Semcom for saving radio transmission energy by sending far fewer bits, but that efficiency is not free.
Not at all. The energy trade-off is stark. We are trading radio frequency power for GPU power. Running dense, multi-layer neural network to encode and decode latent tensors in real time requires massive computational horsepower.
For an edge server connected to the commercial power grid, that might be acceptable. But for a lightweight, battery-operated edge device, the computational toll of running continuous AI inference might drain the battery vastly faster than simply transmitting the raw data over a traditional radio link.
The hardware layer must evolve in tandem with the network layer. We need breakthroughs in ultra-low-power neuromorphic computing and specialized NPUs before Semcom can be deployed ubiquitously across consumer devices. Where is semantic communication actually going to be deployed first, and why?
It's being deployed first in specific enterprise verticals where bandwidth is extremely scarce or where latency is absolutely critical to safety and operation.
Which makes total sense financially. These specialized vertical ecosystems are the primary 6G monetization targets for technology strategists. They are where the big contracts are.
Let's look at the first major vertical, the Intelligent Internet of Vehicles, or IOV. Traditional cellular systems fail miserably under high mobility. When two cars are passing each other at 80 miles an hour, the radio waves distort due to severe Doppler effects, and the network topology changes so rapidly that classic connections drop.
But semantic comms use knowledge graph to transmit high-value triples, tiny logic statements. By using advanced reinforcement learning algorithms like MPDQN, the semantic network stabilizes the training under rapid change and achieves achieves an 85% end-to-end success rate in emergencies where 5G would completely fail.
The second major use case is industrial automation and digital twins. Modern factory floors require near-zero latency to keep robotic assembly lines moving.
And they use RIS for this, right?
Reconfigurable Intelligent Surfaces, or RIS. They are essentially smart mirrors that bounce radio waves around obstacles. By transmitting only the task-relevant deviations, or deltas, semantic networks ensure absolute stability in incredibly complex, noisy electromagnetic environments like a factory full of welding machines.
And the third major vertical is the metaverse and immersive XR. Federated semantic communication is being used to train semantic digital twins right at the edge of the network. This allows the system to achieve incredibly minimal distortion, a measured score of just 0.055 to render massive, real-time holographic streams to a VR headset, all while keeping the user's raw visual data completely private because only the latent features are transmitted.
And what's crucial is that the network performs a joint optimization of semantic compression and transmission power based entirely on the specific vertical's needs. A robotic arm welding a car frame and a VR headset rendering a video game are optimized completely differently by the same tower.
What's so satisfying about those use cases is that they perfectly illustrate Warren Weaver's level C effectiveness. The network is no longer being judged on connection speed or megabits per second. It's judged entirely on whether the car stopped in time, whether the robotic arm moved precisely to the millimeter, or whether the hologram rendered flawlessly without making the user dizzy.
Shifting the entire global communications infrastructure to intent-aware communication opens up a massive, terrifying can of worms regarding risks, trust, and security.
The security perimeter completely shifts. In a semantic network, you aren't just sending encrypted ones and zeros that represent pixels. Semantic representations are highly sensitive because they correlate so intimately with the original intent of the user. You're transmitting the thought process of the machine.
And enterprises simply won't deploy semantic networks if they feel exposed. If a competitor can intercept the latent representations of a manufacturing formula or the real-time intent of a shipping fleet, the technology is dead on arrival.
The major strategic threat is the model inversion eavesdropping attack, or MIEA. This is where an attacker intercepts that tiny, latent mathematical seed flying through the air, and because they have access to a similar generative AI model, they reconstruct the original source data. They steal the painting by intercepting the brushstrokes. So how do we defend against this?
There are several defense mechanisms currently in development. First is KPFUDJSCC. It uses traditional Diffie-Hellman shared secret keys, but instead of encrypting the final digital file, it applies lightweight, mathematically reversible transformations to the latent tensors inside the neural network. It essentially scrambles the meaning itself before it ever hits the antenna without requiring the massive AI models to be completely retrained for every transmission.
Second is privacy-preserving federated learning. Because devices only share the mathematical gradients, the lessons learned, and never raw identifiers, highly private data like factory telemetry or personal health records never actually leave the edge device.
And to address your earlier, very valid concern about hallucinations causing accidents, the networks deploy hallucination filtering. They use cross-domain fusion, basically checking the AI's output against multiple different types of sensors to catch and filter out semantic noise or fabrications generated by the large model-based knowledge bases. This ensures the final output is rigorously grounded in physical reality. Plus, as we discussed, we always have that classical bitpipe fallback mechanism for critical verification.
Let's bring all of this deep science down to the bottom line, economics and business models. Because none of this happens if it isn't profitable. This is a profound hardware paradigm shift. Bit-centric 5G systems are bandwidth-bound. They need more spectrum. Semantic systems are compute-bound. They need more processing power. We are actively moving away from general-purpose CPUs and GPUs toward neural processing units, or NPUs, and highly customized ASICs built specifically for AI.
Which is a vital transition for the telecom industry. Carriers are in a crisis. They must reconcile exponentially rising data consumption with entirely stagnant telecom revenues. Customers want 100 times more data, but they refuse to pay $1 more on their monthly cell phone bill. Consequently, telco operational expenditure, or OPEX, is currently 4 to 5 times higher than their capital expenditure, or CAPEX. They are bleeding money just keeping the networks running.
But wait, if semantic communication reduces transmission overhead by 99%, how do carriers make money? If AT&T charges by the gigabyte and Semcom destroys the gigabyte, doesn't semantic communication completely destroy their revenue model?
It destroys their old revenue model. Strategically, they are shifting from pricing raw bandwidth to paper insight models. They will no longer charge a factory for how much data they use. They will charge for guaranteed task success and highly specialized semantic-aware quality of service tiers. They monetize the intelligence, not the pipe. Furthermore, semantic communication drastically lowers the internal cost per bit by reducing the volume of data sent over massively expensive licensed spectrum. It also enables deep infrastructure sharing. The research highlights that 6G RAN slicing, where operators share the AI infrastructure dynamically, can reduce their capex by up to 68%.
That is a massive financial incentive. And to make this work on the devices we carry in our pockets, hardware, software, co-design is everything. Can't run a massive AI on a phone without melting the battery. But specialized NPUs offer 35 to 70% lower power consumption than traditional GPUs. They are perfectly optimized for the specific INTA quantization math that neural networks use. The sources show systems using what they call LMN.NPU offloading, which reduces large language model pre-fill latency by an astonishing 22.4 times. That incredible efficiency is literally the difference between a viable 6G handset that lasts all day and one that drains its battery in 15 minutes.
This transition is mapped out across 3 distinct deployment phases.
The first is the foundation phase, occurring roughly between 2026 and 2028. We are entering this phase now. This is the critical period where semantic communication transitions out of academic theory and into pre-commercial prototyping and standardization.
We are already seeing the physical proof of concept.
Using software-defined radio testbeds, they are actively proving that semantic encoding can drastically lower transmission energy and reduce latency for specific high-value tasks like robotic control and holographic telepresence. However, the primary goal of this foundation phase is for the standards bodies to agree upon a unified evaluation framework.
Because if the industry cannot agree on how to mathematically measure task success rate or age of information as replacements for bit error rate, nobody can write a procurement contract. You cannot buy, sell, or regulate equipment if you cannot objectively prove its performance.
Phase 2 is the scale phase, projected for 2028 to 2032. Assuming the evaluation metrics are standardized, this is when we expect to see mature semantic network slices and semantic RAN controllers deployed in live commercial environments.
But it won't be on our smartphones yet. The research suggests these early deployments will be hyper-focused on high-value enterprise use cases. We will see them in private 6G networks managing automated smart factories, coordinating massive drone logistics fleets, or managing closed-loop autonomous transit systems.
And finally, we reach the maturity phase, extending from 2032 to roughly 2035. As we approach 2035, the strategic vision predicts that the global cellular infrastructure will have completed its transition. Networks will shift entirely from entities that merely move data to entities that actively participate in the collective intelligence of society.
Which brings us perfectly to the strategic outlook. We are looking at the most significant wireless evolution since the leap from analog to digital. We're finally solving the looming spectrum crisis through intelligence rather than brute force. Leaders must prioritize 3 distinct pillars for 6G readiness. Number 1, unified theoretical frameworks. We must invest heavily in semantic information theory to ensure we can build standardizable, interoperable protocols. We have to move away from fragmented, proprietary black box neural networks that can't talk to each other. Number 2, AI-native edge cloud integration. We have to master the compute connectivity continuum where local edge extraction meets tower-level physical layer control. And number 3, hardware acceleration roadmaps. All product development must align with NPU energy efficiency and AI-native chipsets.
And as we noted, the immediate focus is engaging deeply with the 3GPP Release 20 and 21 standardization processes right now and investing heavily in the knowledge base infrastructure that will power this. So if you had to distill everything we've explored today, from Claude Shannon to AI hallucinations, into one core takeaway for the decision makers listening, what is it?
It is simply this. Prioritizing the transfer of meaning over the transmission of bits is the absolute cornerstone of the next era of global connectivity. It is the only mathematical and economic way we scale successfully into the 2030s.
It's an incredible technological shift to witness.
Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their strategic implications. Click the links below to learn more. Thank you for taking this deep dive with us. Keep exploring and keep asking questions about the hidden architecture of our digital world.